We have already analyzed this two-state Markov chain called on and off chain. There we could actually do explicit computations, which then led to some results about long-term behavior, limiting results, etc. But of course, it's not possible to do similar things for general Markov chains. Such explicit computations are absolutely impossible. If not just difficult, they are absolutely impossible. So to do long-run analysis of Markov chains, we have to come up with other ideas, not computation-based. So that's what we're going to start. And the whole thing starts with the very first idea is that of classifying the states of the Markov chain into two different categories. And we'll see that the two different types of states, these two different classes of states, behave pretty differently in terms of long-term behavior of the chain. We start with what is known as classification of states. As we said that our main interest is in finding or examining the long-term behavior of a chain in general, taking a cue from what we saw for on and off chain. But it turns out that for that understanding or analysis, classification is a very important concept. So consider a Markov chain on state space S with transition matrix P. What we're going to do is we're going to classify the states into two types, and they will play very different roles in the long-term behavior of the chain. So towards this end, we start with some definitions. First, stating time of a state and number of visits of a state. So fix any state x in S. We define two quantities. T sub x is minimum n greater than or equal to 1 such that xn is x, and n sub x is number of n's greater than or equal to 1, xn equal to x. Of course, in the definition of Tx, notice that the set of n's greater than or equal to 1 such that xn equal to x may be empty set if it so happens that the Markov chain xn never hits the state x, then there is no such n, so it's an empty set. So what is the minimum of empty set? We follow the convention that minimum of empty set is infinite. Okay, so from definition it should be clear that T sub x represents the time of first visit. Emphasize that it's not counting time 0 because all times are greater than or equal to 1. So it's the time of first visit to state x, not counting time 0, and nx is the total number of visits, again not counting time 0, to the state x. Now these two play a very important role in our further analysis. One thing is clear that both T sub x and n sub x are random variables, with Tx taking values in 1, 2, 3, etc. positive integers, but it can also take the value plus infinity. As we explained, if there is no n greater than or equal to 1 such that xn is x, in that case Tx is minimum of empty set and we define it to be infinity. Nx takes values in 0 because it may so happen that, as we said, the set of n's greater than or equal to 1 such that xn is x could be empty. In that case, nx is 0, there are no elements there. But it could be 1, 2, 3, and it could also be infinite, which may happen if there are infinitely many n's such that xn equals x. From the definition, it's clear that the events Tx equal to infinity and nx equal to 0 are same events, because they basically represent the situation where the set of n greater than or equal to 1 such that xn equal to x happens to be empty set. Of course, by taking complements, you can see that the set or the event Tx finite and nx greater than or equal to 1 are same events. Now we define very, very important quantity for a Markov chain. It's called the hitting probability. So for x and y in S, and I emphasize that even though I'm using xy, I'm not saying that they should be distinct. So it could be that x and y are same states. So anyway, for xy in S, denote rho xy to be the px probability that ty is finite. Remember, px is a notation for the conditional probability of any event given that the chain starts at x. So rho xy therefore represents the probability that the chain ever visits the state y at some time greater than or equal to 1, given that it starts from state x. Loosely, you can think of it as probability of hitting y starting from x. Suppose we denote rho xy super bracket n to be the px probability that ty equals n for n equal to 1, 2, 3, etc. Then it's clear that rho xy would be the sum of rho xy n when the sum is taken over all possible n greater than or equal to 1. That's because the events ty equal to n for different n's are disjoint, and if I take the union of these events, I get the event that ty is finite. The event tx equal to n implies, but may not be implied by the event that xn equal to x. Remember, tx equal to n means n is the first time that the Markov chain visits x. That is, it is the first n such that xn equal to x. So if tx equal to n, then certainly xn equal to x, but there is an additional restriction that none of the previous xn's, xk's, could be equal to x. So x1 is not equal to x, x2 is not equal to x, xn minus 1 is not equal to x, and xn equal to x is exactly what the event tx equal to l represents. So therefore it's clear that tx equal to n implies xn equal to x. Therefore the probability of the first event would be less than or equal to probability of the second event, conditioned on the chain starting at x. So now we define this classification of states into recurrent states and transient states. So the definition is, a state x would be called recurrent if rho xx is 1 and is called transient if rho xx is less than 1. So let's see what it means. It means, well, a state therefore x therefore is recurrent really means that if the chain starts from 1 x, then it's sure to return to x, whereas that is the probability of returning to x given that it starts from x is 1. While if x is transient, what that means is that for the chain starting at x, the probability of returning to x is not 1, is less than 1, which essentially means that there is a positive probability of never returning to x. So that's the difference between recurrence and transience. So just saying the same thing in a different language, if a state x is recurrent, then the definition says that a chain given to start at x is sure to return to x at least once. However, it turns out, and we'll actually prove this, that something stronger is actually true. What is it? It turns out that if x is a recurrent state, then its chain starting at x actually makes an infinite number of returns to x with probability 1. Remember, the definition said that the chain is sure to return to x at least 1. But what we are saying is that in reality what is going to happen is that if x is recurrent, then a chain starting at x will actually return to x infinite number of times with probability 1. Does it seem surprising? Well, think about it carefully and you would see that this emerges as a natural and only consequence of Markov property, carefully used. Why? Because if a chain is recurrent, that means if a state is recurrent, state x is recurrent, that means that the chain starting at x is going to return to x with probability 1 at least once. But the moment it returns to x once, then from that point onwards, the chain behaves as if it's a new chain starting again at x. So it's going to return to x again. Now you repeat. But this argument has to be carefully made. Well, what we'll do is we'll prove a basic result, which will not only give the above result, but lead to a much clearer picture of the difference between recurrent and transient states in the long-term evolution of the chain, as mentioned already. So here's the proposition. Take any two states x, y in S, and once again I insist that they need not be thought of to be two distinct states, could be same. Then, for any m greater than or equal to 1, the px probability that ny is greater than or equal to m is rho xy times rho yy m minus 1. So this gives a formula for the chain conditioned on starting at x to visit the state y at least m times. So that's what the probability on the left hand side represents. Let's see. Of course, this is trivial for m equal to 1. Because for m equal to 1, the px probability of ny greater than or equal to 1 is same as px probability ty is finite. Because the events ny greater than or equal to 1 and ty finite are exactly identical events. And therefore, it's equal to rho xy. Now we give a heuristic for m greater than or equal to 2. Consider just m equal to 2 for example. Let's see what does the event ny greater than or equal to 2 means. That is, the number of visits to y is at least 2. This clearly means that there has to be a first visit to y followed by at least one more visit to y. Now the probability of there being a first visit to y conditioned on starting from x is clearly rho xy. and then conditioning on the history up to the time of the first visit to y, the probability of there being at least one more visit to y should be Markov property, same as the probability for a chain starting at y to make at least one visit to y, which is rho yy. Because once you condition on the history after the time of the first visit to y, at that present time the chain is in y. So it would be like a chain starting at y makes at least one visit to y. But this is not a proof. Why? The reason is, this is something that one should very clearly understand. Remember, the time of the first visit to y is a random time, while in our definition of Markov property, we can only condition on history up to a non-random time n. So that's the main loophole in the argument that we have just seen. So that's why I only call it heuristic. The actual proof, of course, takes care of this by decomposing according to the time when the first visit to y actually occurs. So here's proof, formal proof. Well, as we've already seen, there is nothing to prove for m equal to 1. So now consider m equal to 2. So as seen already, the event ny greater than or equal to 2 means a first visit to y followed by at least one more visit. Decomposing according to the time when the first visit to y happens, it must happen at some time n equal to 1 or 2 or 3, etc. Decomposing this event ny greater than or equal to 2 according to the time n when that first visit happens, we can write this event ny greater than or equal to 2 as a union over n of these events, that ty is n, that is the first visit to y takes place at exactly time n, and xn plus k is y for at least one k greater than or equal to 1. Now, clearly, if you look at the events, ty equal to n, for various n's, these are disjoint events, because the first visit to y cannot happen simultaneously at two different time points. So therefore, if I look at the probability on the left hand side, of course the conditional probability condition starting on x, then that will be the sum of the conditional probabilities of the events for each n. That's exactly what this says. Now, recall that px is just a notation for this conditional probability. And what we're going to do is, we're going to apply, so the summons, in the right hand side, each term is a certain conditional probability of whatever we have written down, conditional probability of that given x not equal to x. So what we do is, we are going to apply property CP3, and what we'll get is this. So px probability of ty equal to n and xn plus k equal to y for some k greater than or equal to 1 can be broken up as probability of ty being equal to n given x0 equal to x times probability that xn plus k equal to y for some k greater than or equal to 1 given x not equal to x and ty equal to n. This is one of those properties of conditional probabilities that was listed earlier. Now, the first factor clearly by definition is rho xy super n. We are now going to handle the second factor. For the second factor, we try to expand the event that ty equal to n. We know what it means. So the second factor on the right hand side then equals conditional probability that xn plus k equal to y for some k greater than or equal to 1 given x not equal to x, and then the rest of it that is written there is simply an elaboration of ty being equal to n. Namely, xn is equal to y, but xj is not equal to y for any j between 1 and n minus 1. Now, by assumed Markov property, this clearly equals the conditional probability that xk equal to y for some k greater than or equal to 1 given x0 equal to y. Because all this past history, because you are conditioning on xn equal to y and history of the past, and the conditional probability, the event whose conditional probability you are interested in is an event of the future after n. So therefore Markov property applies, and we end up getting this, which of course is same as py probability that ny is greater than or equal to 1, which is rho yx. So we have therefore proved that px probability that ny is greater than or equal to 2 is the sum n equal to 1 to infinity, the product of these two things, and then rho yy comes outside, and the sum of rho xy n over n equal to 1 to infinity is simply rho xy. And this was to be proved, at least for m equal to 2. Proof for general m can now be completed by induction, and you should actually seriously do this as an exercise to make sure that you understood the main idea. Here are some interesting consequences. Suppose y is recurrent. Then what do we have? For any x, px probability that ny is greater than or equal to 1, greater than or equal to m, is in general rho x y into rho yy to the m minus 1. But that second factor would be 1 because y is recurrent. So therefore, px probability that ny is greater than or equal to m would be equal to rho xy for every m greater than or equal to 1. Right hand side doesn't depend on m. Therefore, if I take the limit of this probability as m goes to infinity, the limit would be rho xy. But now notice that the events ny greater than or equal to m, as m increases, this is a decreasing sequence of events, and they decrease to the event ny equal to infinity. And therefore, by continuity property of probability, we obtain that px probability that ny equal to infinity equals the limit of px probability of ny greater than or equal to m, which is rho xy. In particular, if I take x to be same as y, then what we get is py probability that ny equal to infinity is rho yy, which is 1 because y is assumed to be recurrent. And this is exactly what we had claimed earlier. Remember, we claimed that if y is recurrent, then conditioned on starting from y, the number of visits to y would actually be infinite with probability 1. So the definition of recurrence simply required that there is at least one visit to y with probability 1, but in reality it turns out that there would be infinite number of visits to y if y is a recurrent state, infinite number of visits to y starting from y with probability 1. So that part has been obtained as an easy consequence of this result. Next, let's look at transient y. In case y is transient, note that rho yy is less than 1. And what happens? That means that if I look at px probability that ny greater than or equal to m, that is given to be rho xy into rho yy to the m minus 1. And as m goes to infinity, this goes to 0 because rho yy is less than 1. Which means that for any x, px probability that ny is infinite is 0. Equivalently, by going to the complement, for any state x, px probability that ny is finite is 1. Okay, so what are the main takeaways? If y is recurrent, then the following. If the chain starts from y, it will return to y infinitely often with probability 1. That's the first thing. In general, if the chain starts from any state x, y is still recurrent, then the probability of y being visited infinitely often is the same as the probability of at least one visit, which is given by rho xy. Suppose y is transient. Then, no matter which state x the chain starts from, it will, with probability 1, visit y only a finite number of times. The number of visits, of course, could be random. Okay, so these are the main takeaways from that little proposition. We next move to another important quantity, which is the expected number of visits to a state y conditioned on the chain starting from a state x. So, E sub x, ny. Well, let's first look at y recurrent. Not much to do. Why? Because as already seen, given that the chain starts at any state x, ny takes only two values, 0 and infinity. Because if y is recurrent, then no matter where you start, if you visit y even once, then you visit y infinite number of times, or else you don't visit y at all. So ny takes only two values, 0 and infinity, and the respective probabilities are rho xy and 1 minus rho xy. So in this case, calculating the expected value is fairly straightforward. It follows that ex of ny would be infinity or 0, according that rho xy is positive or rho xy is 0. In particular, of course, since if you take x to be equal to y, in which case rho iy is 1, so ey of ny is infinite. Next, look at the transient scenario, when y is transient. Now we already know that for any x, px probability that ny finite is 1. That is, ny is a random variable taking only non-negative finite integer values. So we want to calculate the expected value of this. We quickly recall a standard fact you have seen in undergraduate probability. For any non-negative integer valued z, here is a formula that is often very useful. Expected value of z can be computed by the sum of the tail probabilities. Probability sum m equal to 1 to infinity, probability z is greater than or equal to m. So I'm going to use this for calculating the expected value of ny conditioned on starting at x. So using this, one gets that for any x, ex ny, conditional expectation of ny given the chain starts at x, would be given by So I'm using exactly that sum of tail probability formula, n equal to 1 to infinity px probability that ny is greater than or equal to m, for which we have a formula given by that proposition, which is this, and that rho iy to the power m minus 1, rho xy of course comes out of the summation, and then it's a geometric series, and since rho iy is less than 1, strictly greater than or equal to 0 and less than 1, so that geometric series converges to the sum 1 over 1 minus rho iy, and so this expected value becomes rho xy divided by 1 minus rho iy, which of course is a finite quantity. So we have finite expected value. So the situation for recurrent and transient y's are very different. For transient y, for any initial state x, ex of ny is always finite and given by that formula. Whereas for recurrent, ex of ny can only be either 0 or plus infinity. Now we want to take a different way of looking at ex of ny, and there is a purpose to this. You will see that. For y in S, consider what are called indicator random variables xi n for indexed by n greater than or equal to 1. I say indicator random variables, so they are defined as xi n is 1 or 0 according as xn is y or xn is not equal to y. So xi n is the indicator random variable of the event xn equal to y. Clearly, if I add these indicator random variables over all n greater than or equal to 1, I end up adding the number of visits to y. Each time xn is y, I add 1. So therefore, when I take the full sum, I'll end up getting the total number of visits to y, which is ny. So ny is that sum. And therefore, for any x, if I want to take the expected value of ny, that could be equal to sum over n expected value ex of xi n, but xi n is indicator random variable, so its expected value is the probability of that event, and that is simply pxyn. Now of course there is one issue here that we should not ignore. So in the very first equality, I interchanged ex and sum, brought the expected value inside the sum, and whenever you do this it needs to be justified. Here it is justified because the summands, the random variables xi are all non-negative. Okay, now let's see how this new formula. So what is the formula that we have obtained? The formula that I have obtained is for any x, any y, ex of ny is also equal to summation n greater than or equal to 1 pxy super n. Suppose y is transient. We already know that for any x, ex of ny is finite. But then, from what we have just now proved, this is equivalent to saying that this series, summation n greater than or equal to 1 pxy super n is finite for every x. In particular, if I look at the terms of this series, if the sum of the series is finite, then the terms have to go to 0. And that is true for any x. What happens if y is recurrent? In case y recurrent, we know in particular that ey of ny is infinite, because ny itself is infinite with probability 1. So ey of ny is infinite, which means that the series pyn summed over n greater than or equal to 1 is infinite. Now this leads to a very interesting new characterization of recurrence transients, which is very useful, and we'll see use of it later. So I state it as a theorem. There are two parts of the theorem. The first part is really a new characterization of recurrence or transients. So we state y is recurrent or transient according as the infinite series pyy super n greater than or equal to 1 diverges or converges. Earlier we had given a definition of recurrence and transients, but now this gives you another equivalent characterization of recurrence and transients. If necessary, we may sometimes want to use this criteria to decide whether a particular state is recurrent or transient. The second part says that if y is transient, then of course from the first part we know that the series pyn converges. But in fact something much more is true. For every x, the series pxy super n also converges, and in particular the limit pxy super n is 0. So to sum up, what we have done is we have started with a first level classification of all the states of a Markov chain into recurrent and transient states. And then what we have done is we have seen some properties of recurrent states and transient states. One of the important properties is that if a state is recurrent, then the Markov chain conditioned on starting there actually visits the chain, come back to that particular state an infinite number of times with probability 1, whereas for transient states, number of visits is always finite. But more importantly, towards the end, we got another equivalent characterization of transients and recurrence, which would be extremely useful in sometimes identifying a state to be recurrent to transient, not by going back to the definition, but using this alternative criteria.